Welcome to MA 205 at Bellevue University. We're going to dive right into Chapter 1. Section 1.1 is a preview of calculus. So our objectives are to understand what calculus is and how it compares with pre-calculus, understand that the tangent line problem is basic to calculus, and understand that the area problem is also basic to calculus. So calculus is the mathematics of change. We're looking at how area changes over time, how volume changes over time, how arc length, etc. changes over time, which is different than pre-calculus. In pre-calculus, you have a slope. In calculus, we have a slope that is changing, and we want to be able to do those computations. So it is a little bit more difficult and a little bit more abstract. So here's just a few examples. This is straight out of your textbook of the difference between calculus and pre-calculus. So for instance, with calculus, we're looking at a specific value at a specific point in time, but with calculus, we can take a look at a limit as we approach a certain value. Same thing with slope or secant curve, etc., etc., etc. So you get the idea that we're looking at change rather than static values. There are two basic problems in calculus that you're going to see over and over and over again. And those two basic problems are the tangent line problem and the area problem. So in this lesson, we're just going to be introduced to what those concepts are, and later on we'll go into detail about why we use them, how to solve them, etc. So the first big problem is the tangent line problem. So we know in algebra we can find the slope of a line very easily, but I want to find the slope of a curved line. So how do I do that? So again, we're talking about, this parabola. If I want to find the slope of that line, how am I going to calculate it? So what I could do is take a look at an approximation. So notice I've added an extra point here, and I can look at the slope of this, what is called a secant line. Now again, I'm just using the slope formula that we know from so many classes before this, but that's not quite the same as this line that I'm looking for. I'm trying to find the slope of this line, so how do I find that slope? Well, what if I get a bit closer? So now you can see I've created point R, and point R is closer to P, and it seems that the approximation is closer. So now I have a slope of 5/2, but it's still not exactly correct. So we can see that as we get that point closer and closer and closer and closer to the point where we're trying to actually find the slope, the slope of the secant line will more closely approximate the slope of the tangent line. And so again, as we get infinitely close, and that's the big deal here, is we're going to get infinitely close, we calculate something known as a limit. So our limit is the slope of the tangent line as Q, where Q is that second point that we created, becomes infinitely close to P, and it's going to be the exact value. Now how do we do that? We're going to talk about that later. That's just an idea of what the tangent line problem is all about. The other big problem in calculus is the area problem. And the area problem is essentially how to find the area if we don't have a nice figure like a rectangle or a triangle or a circle. I want to be able to find, say, the area of this shaded region, which isn't easy to find because I have a lot of curves going on. So I want to find what is the area of this region. So again, we're going to look at the concept of a limit. What if I broke that into 4 rectangles? Well, as we can see from this picture, this would give me a good approximation of the area underneath that curve. I've got some areas that are lacking. I also have a little bit of area up here that's being overcounted. So what if I then created more rectangles? So as we can see, yes, this would be better. But again, I want to be exact. I don't want an estimate, I want an exact value. So as I increase the number of rectangles, then my approximation is going to become better and better and better because there's less area missed by the rectangles. And of course, that means I am determining the limit of the sum of the areas. As the number of rectangles increase, the answer for the area, which is called the limit, is going to be my solution, essentially, of the area underneath the curve. So again, the notion of limits allows us to move the point Q infinitely close if we're looking at that tangent line problem, or look at the number of rectangles to an infinite number of rectangles to find the area under the curve. Either of those things, those two basic problems in calculus, have to deal with limits. So we're looking at limits to provide an exact measure rather than the approximations. So again, that's just a preview of what is to come. So in our next section, we'll get started on some basics of calculus.